I grew up in an old house on the countryside that my parents had bought just before I was born. Everything needed to be fixed or upgraded, and my parents did all that by themselves after work. And since my dad was, and still is, a woodworker and artisan, it was clear to him from the beginning that he also wanted to have a workshop on that same property. He also worked as a stonemason, plasterer, and sculptor, and still does on occasion, even though he's technically retired. Growing up in that kind of environment, I knew from an early age that I would want to have my own workshop one day as well, and I certainly also adopted my dad's can-do attitude. And even though I dabbled a lot in my dad's workshop when I was still very small, in contrast to my parents, I was always more drawn to technology and preferred working with metal rather than wood from an early age. On top of that, I also showed an early interest in electronics, which later became an essential skill in acquiring the often super expensive equipment needed for metalworking. When I first started this YouTube channel back in 2014, I did not have a lot of equipment at all. But I set the goal that I would acquire at least one tool or machine each month that would bring me closer to building the workshop of my dreams. Since I would never be able to afford professional equipment otherwise, the plan was set. Buy broken equipment as cheaply as possible, learn to fix it, and pull yourself up by your bootstraps while sharing the results in these little films on YouTube. That was 10 years ago, and I did a lot of that. But I feel like it's been a while since I really added important new equipment and abilities, and I will change that from here on out. This is why we're going to work on this AC-capable TIG welder that will allow me to weld aluminium in this episode. And another recent purchase is this broken plasma cutter that I will repair in this episode as well. But in order to use that plasma cutter, it will be necessary to build a bigger, more powerful air compressor for the shop as well. So we're going to do that today as well then. And over the next few months, I want to tackle another milestone as well, and that will be to build a CNC cutting table for this plasma cutter. In order to look for parts for a compressor and possibly for the CNC build, I hit the scrapyards once again, so let's see if there's anything here that we can use for those projects. So as luck would have it, there are actually several compressors at this scrapyard today. This certainly doesn't happen all the time. This is a German Kaiser brand compressor from the 1960s. This particular style of compressor is extremely noisy though, and it is just too small for what I have in mind. Over here are 3 more compressors. 2 of them are of really low quality though. This third machine here, however, has a bunch of key components that I can salvage. I already have this 90-liter tank that is only a few years old, as well as a brand new triple piston compressor pump, and a big induction motor that I also found at one of the scrapyards a while ago. Combined with this piece of equipment, I should be able to build a compressor powerful enough for the new plasma cutter. And over here a local company has dumped a huge pile of unused nuts, bolts and washers, and I actually took the time to sift through most of it, and I bought a good chunk of it. And we will need some of these parts for the support of the CNC that I've been talking about. In this huge pile of stampings here, I was also able to find a bunch of metal sheets that I can cut with the plasma cutter once it's running again. So with this welder, plasma cutter and compressor build, we have more than enough to do, so let's head back to the workshop then. The support that I'm going to build soon will be made from rather oversized steel tubes and girders that I found, you guessed it, on a scrapyard. And these M16 and M20 bolts, nuts and washers are just the right size for that job. And what you see here on the bench would easily cost you a couple of $100 by now. But it will still take a while until we will actually need these parts. So let's have a look at our first patient of the day then. I recently purchased this welder that I found online for 250 euros. The guy assured me that it's working fine and that all it needs is a new hose package. But I've been buying stuff on eBay since I was a teenager, and I hear this kind of talk all the time. "It always worked just fine" is a typical sentence you will read in the description, and it's always a gamble to pay money for something like that, to be honest. But if you would go to a Lorch dealership, and that is how you pronounce that brand name, and would look for the current version of the Lorch HandyTIG 210, you will find out that a brand new AC and DC TIG welder by this company will cost you around 3,000 euros, and that is without any additional equipment. So I invested another 200 bucks then into a new hose package, so I'm 450 euros in here, and just hope for the best. Still, before actually turning it on, it might be worth having a look inside. Upon removing the cover, we can see that there is a lot of dust inside. One of these blue capacitors also has a date code from 2002. Upon trying to blow out some of the dust, I realized that one of those blue capacitors had actually come loose, and we'll take care of that in just a minute after we have inspected the rest of the device. Upon removing this bottom cover, I blew out the dust from under there as well, and I could not see any other obvious damage or signs of overheating anywhere. In order to replace the broken capacitor, I will have to lift off the uppermost circuit board, and in order to do that, it seems like I will have to desolder these 4 leads here as well. They connect to 2 temperature probes that are attached to some of the big heat sinks below. And after unplugging this connector, I can try to lift the circuit board high enough to be able to desolder the remaining capacitor and also the broken off leads of the other cap, because I decided to remove both of them. The 2 capacitors are part of an EMI or electromagnetic interference filter on the input side of the welder. That means that they are connected between hot and neutral, and the welder could probably work without them. However, the welder might cause issues with sensitive devices that are being operated nearby. And in case you want to replace a capacitor like this, which is a rather typical fault, it's important that you're able to understand what these numbers mean. It is a capacitor with a capacitance of 2.2 microfarads with a tolerance of 10%. And the capacitor is rated for a voltage of up to 400 volts AC. When replacing it, it is important that the new capacitor is also at least rated for that same voltage rating. A higher voltage rating, like say 1000 volts, is no problem, you just don't want to go below the 400. Generally speaking, your replacement should have the same capacitance though, even though in this case a slightly higher or lower value probably wouldn't be an issue. MKP is the capacitor technology that is used here. It's a metallized polypropylene capacitor. It's abbreviated MKP because it's based on German terminology though. Especially in this application, you will often find Class X capacitors marked MKP X2 or similar. They are specifically designed to be connected between line and neutral in these filter circuits and are not to be confused with Class Y capacitors. And since I don't have an exact replacement here, I decided to solder one 4.7 microfarad capacitor onto the board, replacing 2 2.2 microfarad capacitors that had been connected in parallel. When you connect capacitors in parallel, their capacitance simply adds up. 4.7 is a little more than 4.4, but that really shouldn't make a big difference here. With this being done, I also took the time to apply some hot air to parts of the enclosure and peel off some of the rather nasty looking stickers. And I guess it was time for a test now. And that test will be performed in just a few minutes when we will use the new welder to modify a part we need for that compressor I want to build. As you might recall, just a few months ago I uploaded an episode in which I repaired and rebuilt 3 very different compressors, and those compressors have been in constant use since. However, I'm now planning to operate big plasma cutters here in the shop, and that requires a lot of airflow volume. In English-speaking countries often colloquially referred to as CFM, which is short for cubic feet per minute. This old compressor would probably not deliver enough volume of air per unit of time for this purpose. However, I can strip it for parts and complete a collection process that started several years ago. This 90-liter air tank and motor have been salvaged years ago, and a big pump was purchased specifically for this purpose. This ancient homebrew compressor here has the missing parts to finally bring it all together. And as you can see here, my first step was to separate the actual compressor assembly from the tank. The old tank is too small for what I have in mind here, and it could also be dangerous to reuse a pressure vessel that might well be 60 or even 70 years old. It's going back to the scrapyard. And everything here is covered in a thick layer of oily grime that I will start removing in just a minute. and upon freeing the nameplates, I found out that this old AEG induction motor, despite its considerable weight, is only rated for 800 watts, which is probably not enough to drive the new triple piston pump. The old compressor pump, however, is actually a valuable find in itself, and I will probably give it to someone working in car restoration, as it was salvaged from either an old truck or tractor that had a Bosch pneumatic brake system, and this part, well, might be from the 50s, maybe even earlier. The old safety valve and three-phase pressure switch might be a little too old to be trusted. The V-belt, on the other hand, I think has a lot of life left in it. And before even applying any detergent or degreaser, I do my best to simply scrape off thick lumps of dirt from the surfaces here. The motor's fan seems to hit the fan guard in one place, and I'll take care of that in just a minute. The cage or guard and the old support or equipment deck that connects motor and pump are the two main parts that I wanted to salvage here, and that were still missing to build my big compressor. These parts are in a really disgusting condition though. Only chemical degreaser allows me to slowly reveal what is left of an old blue paint job. The same goes for that old Bosch pump, and since even that wasn't enough, the steam cleaner was called to action once again. Upon detaching the fan guard from the backside of this AEG brand 3-phase induction motor and cleaning the blades, I was able to have a closer look at the dents that caused the sound we heard a minute ago. A self-made punch is used to even that out until the motor can spin freely again. But since we are not going to reuse these old components, but rather install a new bigger pump and way more powerful motor, the equipment deck needs to be modified to some degree. The steel parts holding the old motor protection switch are cut off and the welds are ground down. A new set of holes was also drilled to hold the bigger pump in place. And the replacement motor also needs to be modified to some degree. Since I found it on the scrap without a fan guard, we will use the guard that I just worked on a minute ago and bolt it to the back of this 2.2 kilowatt induction motor instead. Measurements are taken and I punch mark the motor in 4 spots, where new holes are then drilled using the drill press. This is necessary so that the motor shaft will be positioned correctly to accommodate a pulley that aligns with the pulley driving the pump. This entire project shows once again that collecting the right parts is maybe less than half the job. It takes much more time and effort to make everything work and fit together. Everything needs to be customized and adapted until everything fits, and there is still much more of that coming. After wire wheeling the equipment deck down to the bare metal, we can try to adapt it to the compressor tank. As you can see, it basically fits on top of the tank just fine, but we will have to weld some additional pieces of steel on here so we can actually bolt it down. For that, a piece of flat stock is first wire wheeled with an angle grinder. Then a set of calipers and a scribing iron are used to draw lines, also using an angle, where 4 cuts are going to be. And then you also have to add 2 millimeters or so for the material that is going to be lost during the cutting action. In the same step, 4 drill holes are also prepared with a punch mark, before the pieces are then actually cut and drilled using a drill press. Holes are usually pre-drilled with a small drill, here 6 millimeters, before they are then widened to 10 millimeters. After that, a countersink is used, to round off the edges of the drill holes. And I do that with a cordless drill here because my drill press can only run at very high speed. And then last but not least, a bench grinder is used to round off all the edges. And the parts are now ready to be welded to the support, which we will do with the new Lorch TIG welder. The 4 parts are held in place with screw clamps. It is then common practice to tack weld the parts in place for creating actual seams. The more heat is introduced into the workpiece, the more warping is also going to occur. Many people probably wouldn't even weld actual seams for something like this, but the compressor pump will send lots of vibrations to this part, and I'm also trying to get a feeling for the new welder here. All in all, I probably set the welding current a little too high here, but even though I still need to develop a feel for this machine, I like the way it welds, and in my opinion is way smoother than my other TIG welder I've been using for the past 10 years or so. I wish I had bought a machine like this a long time ago. In the next step, the equipment deck is bolted to the tank, and then the new pump is bolted to the support as well. And here is where the adaptation and customization process continues. Even though I have lots of pulleys in storage, it would have been sheer luck to just have a pulley with the right outer and inner diameter just lying around, so I made one with a 3D printer. I know that some of you out there will say that this is a terrible idea, and you would be right about that. But more about that in just a second. And as usual, no air compressor project can ever be completed without going on a wild goose chase for a weird adapter piece, of course. In order to make my life a little easier, I decided to try to use one of these hoses here to connect the pump to a check valve that I had already screwed into the tank's inlet port. But a problem came up in connecting the hose to the pump's outlet. See, while the threads for the air cleaners and probably of the outlet side of the individual cylinders are just normal 1/2 inch pipe thread, this connector here, where they all are bundled together, has a UNF thread. And to connect the hose, I need an adapter from 3/4 inch by 16 universal fine thread to 3/8 pipe thread. So I first bought this adapter here, but that was wrong. It's 3/4 UNF to 3/4 UNC. Instead, I had to order this part here for even more money, and it eventually fit. In the meantime, though, I made an adapter piece with a 3D printer. It held for the time being, but I don't recommend this. The outlet gets very hot and the adapter could melt, I guess. In the next step, and after belts had been installed, a certain amount of compressor oil needed to be filled into the pump housing. And the hose I talked about was used to connect pump and check valve, in this moment using the 3D printed adapter. The old motor was probably run with a motor capacitor in its last life, and the stator windings were connected in a delta configuration, and I had to change that into a Y configuration to run the motor on 400 volts 3-phase power directly. Even though the connectors of the motors almost always look the same way, at least here in Germany, you will often find instructions of how to do this inside the motor. But in order for the motor to stop running once enough pressure has been built up inside the tank, you require a pressure switch as well. Now I still had this pretty expensive Conde brand 3-phase pressure switch lying around and installed it on this side of the tank, only to find out later that it was broken. So while waiting for a new pressure switch to arrive, I had to help myself with an ordinary single-phase switch that switches a 3-phase contactor, which then switches the motor. For the first test it is not fastened properly, but I later took care of that as well. And in the attempt to put some more tension on the belts, I used a small car jack and, well, applied some pressure until the 3D printed pulley broke, of course. So I decided to do it differently then after all. This aluminium pulley is not a double pulley like the one I printed, but maybe it will suffice anyway. Since its inner diameter is a little too small though, I first had to widen that on the old lathe using a boring rod. The final thing to do was to give the old guard or cage a new paint job and install it onto the support as well. But that paint is still drying and we're running out of time, so we're testing it without the guard installed. Moment of truth. I limited the maximum pressure to 8 bar by adjusting a screw inside the pressure switch. And with the big compressor ready to go, we can now try to bring that big old plasma cutter back to life. So I found this Messer Griesheim brand plasma cutter from the 1980s on an online platform, and before I bought it I did some research and found an engineer in the Southwest who has designed a slightly modified version of the original handheld cutting torch for this very device, and who also happens to sell all the consumable parts you need for the torch. For a 40-year-old piece of equipment, that is not usually the case. He also supplied me with a manual with a circuit diagram. and thank you very much for that. As I said, I did this before buying the plasma cutter, and this is a piece of advice for all of you out there. The best cutter out there could be useless to you if you can't source these consumable parts. So the seller, and that is a completely different person, was asking for 400 euros. But then it turned out, as is often the case, that the device is actually not working. One of the fuses is blown and the cutter just doesn't even turn on. So I was able to get it for 250 instead. But let's get right into it then. Inspect this piece of equipment, identify the components, assess the damage, and find the fault that causes the fuse to blow. And up here we have a small single-phase transformer and a board that carries the driver for the high-voltage generator. Next to it, a number of three-phase contactors. Below it, a high-voltage transformer, three-phase rectifier bridge, and a capacitor. And finally, in the bottom, from right to left, a fan with motor capacitor, a three-phase transformer, a current relay, and a heat exchanger. I also found these modern Vago clamps down here, and I can assure you that we did not have those back in '87. So this must be from an earlier repair job or modification then. And on the other side we find an invoice together with a replacement motor capacitor. The invoice is for the purchase of the cap and it's from 2020. The Vago clamps on the other side were used to connect a new pump for the cooling system. It clearly stands out for looking much more recent than the rest of the device. By the way, there are a number of safety switches here that all need to be engaged for the plasma cutter to work. One is active only when compressed air is supplied by a compressor. This one guards the water pressure flowing to the radiator, and another one is a safety switch that will only close when this protective plastic cover here is installed. And while inspecting this machine there are a few other minor things. This 25 ohm power resistor is cracked. It still works electrically, but I will have to replace it anyway. This power indicator here is also snapped and we're just going to remove it for the time being. Now you don't know what happened to these things before you bought them. And not having a closer look before turning them on might make things worse and even destroy every chance of a repair. I also always try to clean the equipment while inspecting everything. It's like detective work of former repair attempts as well. Now this shield cap, tip and electrode need to be replaced, and I ordered some replacements from that business I mentioned just a minute ago. And while I was waiting for those parts to arrive, it was time to investigate the actual fault and get the plasma cutter running again. So the top one of these three fuses is blown, and rather violently so as it appears. So what I did is to follow the current path of this fuse, and for that I marked the wire behind the fuse with green tape, and it leads directly to the on-off switch in the front. And since it has 4 contacts and not just 2, the next step was to remove this insulating material and measure what the 4 wires actually connect to. While doing that, I found that the switch is broken as well. It doesn't close anymore. So I labeled the 4 wires with pieces of tape, removed the switch and took it apart. The contacts appeared to be charred and worn, or rather burnt off. I was able to find a similar switch on eBay and bought it. But it would take a few days to arrive here, so I installed a temporary switch for the time being. But let's take a step back here. The fuse is blown and the switch is also broken. Some people would now assume, so the broken switch must be causing the blown fuse. I'm afraid that is not the case. See, a fuse blows when there is an overcurrent or in extreme cases a short circuit. The switch, however, cannot really create these conditions, at least when it's not just a molten lump of plastic. Quite the opposite. The switch doesn't cause a short, instead it doesn't even close. So here's my explanation for that. Something else caused an overcurrent and the fuse kept blowing, and whoever worked on the machine then bypassed the fuse with a piece of wire, for example, so that the switch was overburdened and its contacts were damaged. That's my theory at least. So it must be something else then that connects to the output side of the switch, which I have marked here with white tape. And it leads to a tap on this transformer here. And as you can see in this circuit diagram, the switch via our blown fuse leads to the primary winding of the single-phase mains transformer. To be more precise, to the 0 and 380 volt taps. This device is not connected to the neutral conductor, but only to the 3 phases of a 3-phase power outlet. However, some components inside the device require 220/230 volts, which is the voltage between one of the phases and neutral. But since we have no neutral, a tap on the transformer's primary is used for that. The primary winding acts as an auto transformer here. The so far unknown load causing an overcurrent could be either connected to the secondary winding, which has its own fuse, or to something connecting to this primary tab. And two things which connect to that tab are the big fan and the pump of the cooling system, so that is where we have to look next. So what I did is to disconnect the wire leading to these two loads and hook them up to a power cord directly. This will not turn on the plasma cutter, only the fan and the pump. And while we can hear and see the fan starting right up, the almost new looking pump won't budge. It's not spinning at all. And since we found a loose motor capacitor in that bag inside, my next intuition was that maybe no motor capacitor is yet installed. I didn't see one near the pump at least. But that idea turned out to be wrong. There is a capacitor inside this black enclosure. So here is my next suspicion. The capacitor in that bag is used, but it's not old at all. Someone replaced it because the pump wasn't turning. But whoever did that was looking in the wrong place, because upon removing the fan guard here on top, it's obvious that it's not an electrical problem, but a mechanical one. So I removed the pump from the tank and opened the pump housing, only to find that it was stuck due to a little bit of dirt. It's already spinning again, but I took the time to clean it thoroughly. But it would make little sense to just reinstall the newly freed up pump without also replacing the old fluid, which must have caused the pump getting stuck in the first place. I'm sorry, but all these problems here were seemingly caused by lack of maintenance, and the people who are repairing this didn't really put a lot of thought into it. And while draining the canister, we can see how disgusting the old fluid is and how many pieces of crud are actually inside. So I proceeded to clean everything thoroughly. And I refilled the system with distilled water. I will probably have to replace this soon again once all the dirt is freed up. I also have actual coolant on the shelf, but I'm not going to use that expensive stuff until I have run this water here for a while. I have now also taken off the hose on the output side of the heat exchanger to see if the coolant actually makes it through the hoses, the torch and the radiator. And as you can see, we're back in action. The pressure on the hose also engages the little switch on the side as it's supposed to. The fan and pump were then reconnected to the transformer tab, and only now is a replacement fuse put in. In the meantime, the replacement parts for the torch have arrived and have been installed as well, and they fit just perfectly. A replacement on-off switch arrived soon after and was installed as well. Upon turning on the plasma cutter for the first time, the fuse is no longer blowing and everything seems to work fine. So I hooked it up to the compressor and it was time for a test. Yes! So as you can see, the plasma cutter works, and it was a lot of fun to see it burn through the steel with ease. In the meantime, I have already started to source the parts needed to build a CNC table for the plasma cutter, and that will happen over the coming months then. This, however, was all I had in store for you today. Please give the video a like. If this is your kind of content, it would mean a lot to me. So while it might not always look like it, this channel is extremely expensive and time-consuming to run, and I need your help to keep it going. So if you can, please check out the donation link under the video, or maybe consider becoming a supporter on patreon.com/tpai. See you soon.